wine and you guys. I will not say that. What I will do, I will prepare you slowly with not much micrograph so that your eyes won't be strained. I'll prepare you slowly I don't know why it's just automatic. I'll prepare you slowly for the welcome wine which is coming up soon. So yes, Laboni Afroz is very important, who was named the presenter. I'm not Laboni Afroz, she's the lady. She is my PhD student and she did most of the work. So I'm very happy that she was given the credit. So I'm the PhD supervisor, and then I have two co-authors who are from Center for Additive Manufacturing and School of Engineering. Now, what I'm going to talk about is, the title says, we go back to the crack growth similitude laws, which is 50, 100 years back when the Paris started the fatigue crack growth relation. And what we try to do, we try to bring back those similitude laws, which have been researched quite significantly in the last few years, and to see, the hypothesis is, can those similitude laws be applied for additive manufacturing alloys? And I mean not only steel, not only aluminum, not only titanium, which is normally made by AM process, throughout across the range of AM alloys. The benefit is, if we can prove that these similitude laws hold good on how to develop those laws, the benefit is significant, because the similitude laws allows going beyond the Paris regime and include effect of, say, R ratio, processing condition, even manufacturing process, and possibly surface surface. So we can unify all these factors into one equation. And that's the key thing I'm going to talk in a couple of minutes following now. Okay, so I'm from RMIT, and the background is, of course, I will skip that. There are a lot of challenges, and the challenges, what I want to show you with AM is, there are too many factors involved. We have effect of processing condition during AM, we have the effect of powder properties, we have the effect of post-processing condition, including heat treatment, and the microstructure and roughness produced, including the subsurface defects and the bark defects. Now, to take all of this into account, we need to come up with better relationship or correlations to analyze and evaluate AM materials. And our key application is, we want to translate AM-produced materials for critical applications such as particularly aerospace, but also a bit of automotive and marine applications. So this work will thus have relevance because this is well connected with defense. So let's start with, as I said, wine is waiting, so no complications. We know all the age-old fatigue crack growth rule. I don't want to talk about again. So dAdN is proportional to a power law with the material constant C and M, delta K to the power M, when delta K is a stress intensity factor range. Now, what it doesn't take into account of the R ratio, and what happens as a result, if you have a different R ratio, your curve shifts towards left, which means if you have a higher stress, your fatigue life for a given, or crack growth rate for a given delta K would be higher, which is simple understanding. Now, this FCG curve shifts left with the increasing R ratio. What we want to do, the whole principle of similitude law, is to include R ratio within this crack growth rate equation, so that we don't have to consider multiple cracks with this. So to do so, this is the Paris law, and the background of Paris law is, we all know Paris law works well in region 2, which is the stable crack growth region, which is a kind of a power law relationship, holds very good with two material constant, M be the slope. Now, what about happens in zone 1 or region 1, where, or region 3, region 1, the threshold region, the crack growth is controlled by microstructure, R ratio, and environment, and also in region 3, which is a rapid fracture zone, where you get catastrophic or unstable crack growth. So 1 and 3, it's beyond a linear or log linear zone, where the crack growth is dependent on other factors, microstructure, stress ratio, and environment. This feature kind of modified set of Paris law models called Hartman-Shimichi, Walker, Kujawski, etc., which tries to include the effect in region 1 and region 3 so that we can have a unified crack growth loss. Now the plan here is to apply these models or see if these models work for AM alloys. This will give us a great benefit. To do so, what we did, we looked at a number of modified so-called Paris law crack growth models such as Hartman, Walker, Kujawski, etc., which are known as fatigue crack growth similitude laws. Now, let's define what we mean here by similitude laws. It's defined as fatigue crack growth curves of a given alloy. Alloy is same, but we test that different R ratio or environment conditions can be collapsed or condensed into one curve with a modified delta K value, with a modified crack growth equation. So that means the growth rate can be represented by one single mathematical equation, which will make our analysis and prediction of fatigue crack growth easier for different R ratio, different processing condition. So this is the traditional definition of fatigue crack growth similitude laws. Then it will be easy to predict for a different particular alloy for different conditions. Now, I want to mention the work by Jones et al., and there are many papers on that. Why I mention Jones is Professor Les Jones was my PhD supervisor, who made a great contribution in this area of similitude laws. I didn't do PhD on this topic, but I was aware of his work very well. So he used 22 different aircraft materials and showed that these all fatigue crack growth rate equations could be converged or condensed into a Hartmann-Schitz model and found a variant for the equation, the alloy for the scatter. But that was not for LT manufacturing materials. So what we decided to do, we decided to look at these relationships here, Hartmann, Schiff, Walker, and Kujawski, for a range of AM alloys. Normally, we look at titanium, aluminum, and steel to see can they be collapsed into these crack growth laws. And the question is why they cannot be, because there are other effects such as we know additive manufacture porosity, subsurface porosity, porosity size, location type, and microstructures, anisotropy, which are not present in conventional alloys which we deal with fatigue life calculations, right? So that's the idea of doing that. Now the methodology what we did, we used a number of crack growth models such as Hartmann-Schiff model, Kujawski, Walker, and Huang. These are the common 4 modified models, and we tried to apply, we collected lots of data on AM alloys, crack growth data, particularly Hartmann-Schiff has applied with titanium, aluminum, 300M steel, and 31L steel alloys, and then we have used other ones like Kujawski, Walker, and Huang on particular titanium alloy. How we did it? We took this FCG data of AM alloys from literature and replotted with the redefined equations to see if the similitude laws would work or not. And what else we did is, due to limited availability of fatigue crack growth data, that was our problem when we were trying to do so, we used other models for only TI alloys. Now, this is a key thing I want to emphasize. Excuse me. Although the similitude laws include the R ratio and environment condition for the test, this is the standard definition, so far has been used. We want to extend it for different processing conditions during AM and different post-processing conditions, which are normally not included in traditional, conventional cast or forged alloy where the similitude laws have been traditionally applied. So this is the new addition we are doing, and also the build orientation we want to include in the similitude laws. So the methodology is, we use the Paris law first. We convert to Hartmann-Schiff's equation by changing crack growth threshold by crack growth stress factor range minus crack growth threshold, and we use R ratio here. We add a mean stress effect through R ratio, and we add cyclic stress intensity factor range, which also contributes towards the crack growth. So we replace the equation, which is the traditional Paris law, by using Hartmann-Schiff, and we can then able to predict the crack growth along region 1, region 2, and region 3 in a unified way. So, we Hartmann-Schiff's equation modify the Paris law, including mean stress effect, cyclic stress intensity factor, and also the crack growth threshold, and thus it will be unified, or it will be a universal law for all region. And now we want to check, can it be applied to a material? Okay, so let's take the Hartmann-Schiff's model, which is a very well-known model for similitude study. So the Paris crack growth law has been modified. We have a factor D now, and we have a delta kappa instead of delta K. So delta kappa is calculated a modified value of the crack driving force. D is the coefficient which is constant for a given R ratio. Delta K is the crack growth threshold value, which is function of R ratio and crack length, and KIC is this reference 37 defines cyclic fracture toughness, which is a new parameter which also is defined by the material property. Now, these data, delta KTH, max stress intensity factor, and Kc, were extracted from DADN versus K curves, and finally we evaluated this parameter. We plotted this we calculated this parameter for each point using the material property and the Paris law data, and we plotted DADN versus this and calculated by fitting a curve D and alpha value. And we note by this D and alpha value whether similitude laws can be applied. So that was our methodology, how we proceeded with this. So let's see. Let's take AMTI6L 4V alloy, so titanium AM alloy, and we consider these are data mainly from the literature. This is crack growth rate versus delta kappa in this case. You could see for as-built material with 3 different R ratios, and also with annealed material with 2 different R ratios, all the curves for this titanium alloy are collapsed. So different post-heat treatment, different R ratio, they collapse as a single curve, particularly in region 1 and 2. We don't have extensive data in region 1, but region 1, part of region 2 and part of region 1, all the curves collapse, but region 3, we have some issues, particularly for beta annealed materials, they don't collapse, and that we believe due to the annealing effect which changes the microstructure and why we create the discrepancy from the similitude law. But however, the interesting thing is all these different R ratios and post-treated conditions can be accurately represented by a similitude equation, one equation in region 1 and 2. So that means this equation is a universal equation for titanium alloy for a number of AM materials as built, different R ratios, and also beta annealed, which means we can analyze it in one equation. Then let's move to the same thing. We looked at this, all curves are Hartmanship or titanium alloy. All curves are R ratio 0.1. Now we looked at different processing condition, HIP and as-built. And as-builts are 2 different cases, which is crack growth is perpendicular to the build direction, one is parallel to the build directions. And we can see here as an interesting story, the value of D and alpha index are almost same for all as-built curves. So all as-built curves, when you use the modified equation delta kappa, they collapse in one line, or HIP curves. So now the similitude laws are different for different processing conditions, but at least all the HIP curves are collapsing in one, and all the as-built curves are collapsing in one. You can see very close values of as-built values of D and alpha, particularly the slope, are very close for all the curves. Although the D values are different for HIP and as-built, and that's why you can get the shift. So that basically shows us for similar process condition, either HIP or as-built, the variation of the slope is comparatively insignificant, and no significant variation is observed for variation in the build orientation, because you can see all as-builds are collapsing into one curve. So build orientation has not much effect on fatigue crack growth data, which we have observed previously in my presentation. I have shown it for aluminum alloy. Now, let's talk about titanium to aluminum, which is one of our focus. Does it work? Does the similitude law work for aluminum alloy? The answer is to some extent. So we took data from as-built data, platform heated, different process condition, again as-built, and heat treated from these references. And we plotted again delta kappa, the modified stress intensity factor range, including all the other factors I showed you. You can see the value of alpha is between 1.6 and 2.2. Sorry. You can see the value of alpha is between 1.6 and 2.2 for all as-built conditions, and the D values are constant, 6 into 10 to the minus 9. So they are kind of collapsing into one curve, and the heat-treated ones, you have a different alpha and you have a different D value as well. So what it tells us, as long as the processing is the same, you can take into account of the R ratio and environmental effect, and also into an R ratio environmental, particularly into the same curve for a given alloy. But if the given alloy is processed differently, then the similitude law doesn't work yet, what we found. So that's the take-home message from what we get here. Then we looked at steel, because we wanted to do for all cases to see where it acts. And this was the best. We are very happy. For steel, we don't know why. Irrespective of the processing condition also, as built, annealed, hip, as built, both crack growth in the build direction and perpendicular to the build direction all collapse into one curve with a value of alpha between 2.2 and 2.1. Even post-heat treatment and build direction, build orientation didn't much affect the fatigue crack growth in steel, which is a good finding. And this steel is very important, 316 steel, particularly for our applications with defense-related applications, particularly transport. And this can be given by this law. dAdn is d times delta kappa to the power 2.21. So this equation will universally describe the relationship between crack growth rate and delta kappa. Sure, thanks. Finally, we looked at AM 350 steel. Again, the story is slightly different. We found here, this we have to investigate more with microstructure and all. All the processing condition, as built and heat treated, they all collapse into one curve almost for all crack growth perpendicular to the build direction, but the parallel to build direction is slightly different, which we believe due to the strong anisotropic microstructure effect, where the crack growth is arrested significantly in the build direction. That is the main cause of this phenomenon, which we will investigate further, because this data we took from literature. We didn't have our own material tested for that. So this is the thing. Again, the similitude law works, but again, there's a discrepancy for the crack growth growing perpendicular to the build direction where crack is arrested. Finally, just quickly, in 30 seconds, I'll go through the other models. Hartmann-Schiff is the most popular model for similitude law. We looked at Walker model also, where it's the same story, but you express the similitude parameter using delta k divided by 1 minus r, 1 minus yw, where we modified the stress factor range by introducing this yw parameter, which takes care of R ratio on the fatigue crack growth. Now, we use the Walker value 0 to 1, that's the recommendation by Walker, and Walker model is capable of taking R ratio effect on fatigue crack growth only for tension condition. So what happens now, if we apply the Walker model for Ti alloy, you can see excellent collapse, particularly in region 2, but in region 1 and 3 there is slightly discrepancy, and it is found from literature. The best fit curve is obtained with YW equal to 0.5. Crack growth for Paris region, it represents the similitude very well. A wide range of divergence observed at this region 3 and the beginning of region 1, which may be again still to be investigated due to the microstructure effect. But we can see the single equation will represent crack growth law for 3 stress ratio as built and annealed condition. So some cases we can also collapse the same processing equation. The last one, Kujawski model, same factor. We use a delta k star here, which is calculated using this effect. Just 1 minute, I'll finish, don't worry. A delta k plus is 1 minus r k max for r is greater than 0, positive R ratio, tension loading. And if it is a reverse cycle loading, we have equal to k max. And this is a simplified form we use, this Kujawski model. And this model can convert various fatigue crack growth curves at different R ratios. So what we did, let's see how it works. And it worked perfectly well, the Kujawski model also. You can see for different stress ratio and also different processing condition, annealed and as built, the curves collapse, provided the R ratio, if it is less than 0.7, one set of curve, greater than 0.7, one set of curve. And this is already told in the Kujawski model. When Kujawski proposed it, he found it works better when the R ratio is 0.7. Again, it is not well known why it is true. Again, so we have 2 sets of similitude law for different R ratios, and all the curves collapse into one. Finally, the Huang-Meng model, again the same story. I'm not going into details of the model because of time. You calculate with the beta factor and an R ratio, the M factor, and you replace the Paris law by this form, and then we again try to fit this with the fatigue crack growth data. We found moderate correlation in terms of similitude relationship between dAdn and delta k star. So what it shows at the end of the day for all of the study is, this is the summary. What is the positive we found, and we did more investigations, that AM alloys, we can apply fatigue crack similitude laws with a modified form of delta K, which is called delta kappa. And we can collapse all the curves into not one, sometimes in groups, based on processing condition difference, or one case based on R ratio. So if we have that understanding, that will make our fatigue analysis very much simplified. Because we know some of those material properties, delta KTH, KC, critical stress factor, cycle stress factor, R ratio. So we can insert that modified delta kappa and can predict DADN much more easily, and we can integrate DADN to predict fatigue life much more easily. So that helps us for our fatigue analysis, but we need to know these trends from different alloys a priori before you apply. So that's kind of concludes my presentation. Thank you very much. There's a bunch of reference. I would like to thank a lot. And finally, I would like to say, if you come to Australia, if you have a chance, there's a very complex fracture formation in an interesting place called Great Ocean Road. You can see the rocks still being fractured, and you can see mode 1, mode 2, mode 3 in one place.
Which model fits the data?
Then we have to see which similitude law exactly can fit this data. So in that way, I will like to welcome you all to Melbourne. We will host International Congress on Fracture, ICF 16. It's a couple of years away, but I just give you a hint that if you want to have a holiday 5 years later, you're very welcome to visit my city. Thank you very much.
Thank you very much. Super quick.
Yes, a very super, thank you very much, Raj, for your
Thanks so much. Thanks for sticking around so long. I didn't imagine so many people.
But we will have time because the cocktail will be at 7 o'clock in the pool, near the pool. Okay?
Perfect.
Perfect. Just a small question. When you use your similitude laws, use delta kappa. For example, as you know, the Nasgro law, the FN Cape law, uses alpha as you used in delta K.
Alpha, yeah.
And alpha means constraint factor in Newman's law. Does the alpha in your models is the same, is an approximation parameter?
It's very same, but we don't use the same value of alpha. We calculate the alpha by fitting the data with the fatigue cracks.
Okay, they use crack closure,
Yeah.
you use another approach.
But the idea is same, yes.
The idea is the same.
Yeah.
Thank you.
Thank you. Thank you very much. We concluded the section. Thank you to the speaker, all the speakers.